Three open. ഞാൻ അന്നേരം PPT X എന്ന് കൊടുത്തിരുന്നില്ലേ, അതാണോ എന്നൊരു സംശയമുണ്ട്. ഇത് എവിടെ ഇട്ട ഉണ്ണി?
Yeah, good morning, all of you. So I will introduce Dr. Manoj MG. He's a senior scientist in Advanced Radar Research Center at Kochi University, and he has vast experience in meteorology and atmospheric sciences. And he worked in many prestigious institutions as a research fellow, like IISc Bangalore and IITM Pune, and so he had a lot of experience in aerosols, clouds, and dynamic meteorology. So and he has a lot of papers in his area. So he has more than 40 papers, his own contributions. So that is very significant milestone for a researcher. And so I kindly invite Dr. Manoj for delivering the talk. Thank you.
Thank you, Dr. Unikrishnan, and good morning, one and all. So I hope we are meeting for the first time, and you all are from different background, right? So how many of you are from meteorology or atmospheric science? Very few. Okay. Rest are from physics, right? Okay. Physics, remote sensing, okay. Environmental science, okay. So you may be having some idea on vector calculus, differentiation, integration, etc., right? Anybody who is not having any experience in this field? Environmental science, at least plus 2 level maths you are aware of, right? Okay, we need that much. So, okay. So today I am going to describe certain special subjects have been assigned to me. But after coming here, Dr. Unikrishnan told that need not stick to that because very few people have got the concept of atmospheric physics, how instability arises in a fluid. So we need to discuss how a rotating fluid, this is actually rotating along with the earth. So how instability is introduced as a result of thermal forcing or dynamical forcing, etc. How it leads to various weather systems. So we need to just go back into the fundamental ideas of conservation laws. That is only 3 laws. So in that sense, atmospheric science is very simple. We need to know only 3 laws: law of conservation of mass, energy, and momentum. Okay. So having said that, we may think that this is very easy, so that we will be able to predict whether it is going to rain after 1 hour or so. But when it comes to actuality, things are a little bit complicated because of the non-linear nature of the atmospheric processes. Individually, if you take any process, it is almost straightforward. It's like 1 plus 1, you have 2. Okay, straightforward answer. But it is actually true only in the case of mathematics. When it comes to atmospheric science, 1 plus 1 is may or may not be equal to 2. That is the reason. Sometimes it will be 2. Sometimes this one and the other one may get cancelled out. So you will get entirely different answer, 0. Okay. It's like a constructive and a destructive interference. You know, physics background, what is constructive and destructive interference. Sometimes it will interfere in a constructive manner, sometimes perfectly in a destructive manner, sometimes half likewise. So we don't know at what time, at what place these processes, each of the causative processes behind weather formation will add up or will negate or will add up in the negative sense. We don't know. Okay. So in that sense, the atmosphere is a non-linear regime where non-linear processes are acting. Actually, what is this non-linear processes? We need to know. Okay. What is a linear process? We will discuss that later first. What's a linear process? Any idea you have? What is a linear process? Linear means it's just like a line in common man's language or layman language. It's like a line. If I ask you to put 2 dots in a plane, xy plane, and ask you to connect them, you will get a straight line because that is the shortest path. Okay. So if 2 points are there, we can just connect them through a straight line. And if a third point comes in the same slope, then you can just extend it into the future, right? Still that will be a straight line. But I gave you a condition. If it aligns with the same slope, if it doesn't align with the same slope, what will happen? You suppose you are starting from A to Z. Okay, A and Z points are. Now I add a point in between B. How will you reach Z? Through B you have to go. So it may be B may be lying above or below this. So A, B, Z, something like that. Okay. Now if I add one more point, D in between, so you have A, B, D, and Z. How you can go to Z? Either from A, B to Z or A, B, D to Z. There are possibilities, multiple possibilities, right? Yeah, multiple possibilities. Now, subsequently, I add up n number of points in between. Your destination point is Z, starting from A. Okay. what are the possible ways by which you can reach Z? Suppose all this A to Z 26 letters are there, right? So forget about A and Z, rest 24 points are in between. You can either go to A to C, then you can go to B and then D. It is as per your wish, right? So things are now not in a linear manner, right? Zigzag. This is, I just gave you an analogy. This is the case what is happening in the atmosphere. Suppose on a hot sunny day morning you get lot of radiation. As a result of this absorption of radiation, the air becomes hot near the ground. It starts expanding because it is hot, temperature is increasing, it starts expanding. Once expansion happens, the density decreases. Okay, compared to the surrounding area, your area maybe Akullam or NCESS, this region, the air will become buoyant, right? Because it is less dense. Now it will start rising. In between, there can be lot of water vapor concentrated or converging to this point, right? Then the hot air may get lifted up to the dew point level or the what is known as the LCL, you know, all these processes, lifting condensation level, where clouds form starting. But I told very straight, very simple. Things are not so. In between, lot of aerosol particles are required, right? Enough moisture is required. Enough instability should be there to lift the air parcel up to that level where clouds can form. So all these add up, and hope finally you have got a good cloud here. What is the probability that the cloud should rain out exactly at Akullam? When the air parcel or the cloud is about to precipitate, some gusty wind can come and sweep away this cloud, and the rain may be occurring in Tambanur or somewhere else. Okay, so you did all this homework for producing rain. Finally, we didn't get, or we are not going to get any rainfall. Why? Because of this unexpected factor. It's like adding n number of points or n number of positive factors in between. The analogy you remember now. So as we add up more and more positive processes or influencing process or controlling process or governing process, whatever, we use all this synonymously. As we add up all these positive or controlling factors, the final output is a big question mark. You are a meteorologist, you have given forecast that okay, today afternoon there is going to be intense rain with the lightning and gusty wind, probably hail. But NCESS people may not get any rain. Those who are not expecting such a rainfall somewhere else in the periphery or in the Arabian Sea, it can fall somewhere else. What is the use? You produce all the clouds, up to that you are okay. But final twist, final moment, everything changed. Okay, this is some sort of uncertainty adding. So it is like adding n number of controlling factors. As the controlling factor increases, our processes become highly non-linear. How to face this problem? That is the question. So for that purpose, you need to have a good understanding of the physical processes, especially the physics, the radiation, the thermodynamics. Then comes the dynamics. Okay, and what makes the process even complex is certain feedbacks which we may not have thought about or might not have thought about at the initial level, because there can be several feedbacks. Suppose I gave you some idea that okay, a big cloud formed and the cloud persisted for several hours without raining. Okay, so what will happen? The cloud can block the cloud formed around suppose 10 or 11 o'clock, but it is due to some processes, microphysical processes, it didn't rain out. Cloud is still persisting overhead. After some time, what will happen? If that is a deep cloud, this cloud can block the incoming solar radiation. as a result, the cloud, the place where cloud formed may get cool for longer time. So cooler means the pressure will increase. Okay. So the wind actually otherwise should have come to here. The wind may be from here to somewhere else, because this is going to be a cooler place. Some low pressure area may be adjacent. So wind will go to that direction. In that direction, cloud also will drift away. Have we thought about that as a result of blockade of solar radiation by the same cloud? Now the wind pattern changed, or the wind direction changed. So the cloud now moved away from this one. This we didn't think initially. Okay, so our finally what the common people need is whether it will rain or not. They don't want to know whether you are a physicist, dynamic, meteorologist. I don't want to hear about all these complicated technical jargons. I just need you tell me I have a function today evening, whether it will rain near Lulu Mall or Akulam somewhere. Okay, this is the common demand from the people. So now again we will go back to the first sentence. Only three conservation laws, but when we mix up together, the feedbacks make the processes even more complicated, or in terms of technical terms, it becomes non-linear. So to address this issue, we have a variety of tools. We should first have a strong fundamental understanding of how the processes are happening. Then we need to predict the future. Okay, so prediction is becoming, at least we know what is currently going on, but when it comes to prediction, a small error at the initial step can become double, triple, quadruple, etc. It will become manifold, and finally prediction goes wrong. So this is a challenging topic, at the same time inspiring. Okay, inspiring. And let us try, even under this high non-linearity, we are able to predict with a certainty, some sort of certainty we are able to predict it. So for that purpose we need a good understanding of the dynamics, the radiation, the atmospheric physics part, thermodynamics especially. And I am going to talk about dynamics. Okay, actually my PPT is scattered in different PPTs. I didn't get time because yesterday night only I could just to prepare some of this one. Let us see. Those who are online, are you able to hear me and see the PPT? Please reply.
Yes, sir.
Yes, sir.
Okay, okay. So since it was made hurriedly, it may not look very good. So the laws governing the motion in the atmosphere, atmospheric motions are governed by three fundamental laws of conservation, as I said earlier. One is the conservation of mass, and we know mass can neither be created nor be destroyed, although it may be rearranged. It is a redistribution of mass and changed into different types of forms. Then conservation of momentum. Within some problem domain, the amount of momentum remains constant. Momentum is neither created nor destroyed, but only changed through action of some external forces. So here comes the external forcing. External force is required to change. If there is no external force, that process will be in its continuation state. Okay, so external forces are required. Then conservation of energy. Though energy can be transformed from one form to another, it cannot be created nor destroyed. So everybody knows this. Now, when it comes to dynamics, there are two terms. One is the kinematics and the other one is the dynamics. So the term kinematics has its origin in the Greek word kinesis, which means motion. So kinematics, both kinematics and dynamics are related to motion only, but there's a slight technical difference. Kinematics is the study of motion without regard for the causative factor or causative forces. We just see the laws, how they are moving, which direction it is moving, etc. But we are not worried about what force is responsible for this type of motion. Okay. So dynamics is derived from the Greek word dynamis, which means power, and it is the study of the causes and the description of motion. So one way to think about the difference between kinematics and dynamics is that dynamics is the cause of motion and kinematics is the effect. Okay. Or I can say that I can make an equation: dynamics equal to kinematics plus the causative physical processes. Quite often we are not much worried about the causative forces. We just describe the kinematics only. But if we need a comprehensive understanding of the phenomenon, then we need to know the causative factors. So it is possible to study the motion of objects without being concerned with the forces that cause the motion. That means we can study kinematics. But ultimately, scientists want to discover the causes of motion to better understand and to be able to predict motion. That is the, if we know the underlying causative physics, then we can predict if that force changes in time, then there will be a corresponding change in the motion itself. Now we, in atmospheric physics or in general fluid mechanics, we use the concept of continuum. Continuum means what? It is similar to continuous. That means the fluid medium is continuous. You consider this this entire hall as a continuous medium. Okay. You sample some air from that location or this location. It will be having same proportions. Constituents will be in the same proportion. And you can divide, again, you take 1 liter of or 1 meter cube of air. You examine its properties. It is similar to the whole entire whole, right? Now if you again subdivide this 1 meter cube into 1 centimeter cube, you assess the properties. It will have having the same property as the 1 meter cube. Likewise, you can continuously divide until when up to the molecular level, it will having the same this one. So it is a continuous medium, not like a discrete type of, somewhere it is this property, in between some other property, not like that. It's continuous. Okay. So generally in physics we use the Boltzmann equation and Newton's second law, Navier-Stokes equation. All these are based on this Boltzmann equations. So I can say that a continuum is a body that can be continually subdivided into infinitesimal elements with the properties being those of the bulk material itself. Isn't it? Now, what are the different types of fluids in dynamics? One is the compressible or incompressible fluids. So we can give a good example of a compressible fluid. That is nothing but the air that we breathe. We can give another example of a incompressible fluid, mostly incompressible. What is that one? That is nothing but this one, not this bottle, water. Okay, water. So the compressibility actually is an inherent nature of a fluid that will dictate its macroscopic properties. Okay. For example, I will give you an example. If you start from the base or the surface of the atmosphere to the top of the atmosphere, the pressure varies, right? How does the pressure vary in the vertical direction? It's an exponential decrease. Okay. So my question is, you have a say 100-storied building, okay, 100-storied building, one floor above the other, likewise 100-storied building. What is the weight that the lowest floor bear? It is nothing but the weight of the 99 floors lying on the top of it, right? Yeah. Then what is the weight that the second floor carry? 98, isn't it? Likewise, third floor, 97. 99th floor, 1. So how does it vary? It varies linearly. Is it similar to what the atmosphere also carries? The weight of the air column is just one above the other. It is stacked vertically, one above the other. So the pressure also should decrease linearly. Am I correct or not? Now, this is a very tricky question. Why doesn't it decrease either linearly or parabolically or some different forms rather than sticking to this exponential decrease? Has anyone thought about it? Are you getting my? Okay, actually this board also should be there, and I could have. Okay, online participants. Yeah, they told that I can use. Where is the board? Yeah, yeah. Okay. Oh no, no. Here. So online participants are there. Several participants. Can somebody answer with confidence why the pressure is not decreasing linearly, but it chooses exponential decrease?
What is the uniformity matter? Building like
Yeah, building is also uniform. You can think. But
but
only concrete blocks, no air, nothing. I just stack.
when we take a air column,
Ah,
so air is not uniformly inside that column. Suppose that is consider a cylinder.
okay.
So atmosphere is. So air is not uniform inside that. Like it's settling out.
Unique in the sense, what is unique? You tell me.
Uniform means
Yeah, uniform means.
suppose I have a building.
Hmm.
So building made in a suppose 10 floor building.
10 floor building.
So
Yeah.
each floor have like uniformity, not like a density. Like
Okay.
varies.
Yeah.
If air is
Okay, you forget about the air. It is a full concrete stack, full concrete
so
blocks.
density is almost
Okay.
same
Yeah.
inside the
Yes,
building.
yes.
But
Come.
in atmosphere, so if suppose cylinder density.
Yes, he has given the clue now. He has told that for the building, the density is almost the same from first floor up to 100th floor. But for the atmosphere, density is higher near the surface. As we go up, that also decreases exponentially. So my question is, why density decreases exponentially rather than taking a linear decrease path? Tell me. So he has answered partially. Very good. We should appreciate it.
Sir, the solar radiation also
Hmm.
affect. So at top level, if I will suppose I'm considering 10 meter or 10
Oh,
kilometer atmosphere.
okay, okay.
So solar radiation effects means density will be less.
Forget about the solar radiation. It is night time, so no radiation. I will give you. Yeah.
Rotation will affect the earth rotation also.
No, Earth rotation is not going to affect the density. In fact, okay, it can affect the wind direction, etc. Suppose Earth is not rotating, then that problem is also solved. Yeah, very good. Gravity. Then my question is, gravity, same gravity is affecting your concrete building also. So the gravity which affects concrete building is not different from the gravity which is affecting the air density also. Very good. So Sneha was answered finally. Air is compressible. The other one is incompressible. So now you got. We will go back to the fluid. Where are you able to see this slide? Yeah. Oh, something duplicate we have to give. Duplicate slide now. Yeah. So finally we have got the answer because the air is compressible. So you see, in a compressible fluid, the vertical properties is entirely different from an incompressible fluid. So I will give you an assignment. You take the density from radiosonde data and plot it with respect to height. At the same time, you take the density of the seawater, plot with the depth or height, whatever it is. Do you see any difference? So somebody who is from oceanography background, you might have, you are from oceanography. How is your density varying? Not your density, your ocean density. Yeah, density with the depth, density increases but slightly only. Okay, near the surface it is, say for example, 1025 kilogram per meter cube. Below something like a 5000 meter depth, it may be 1028, something like that. Okay, 2-3 kilogram difference only over a 5 kilometer depth. But in the atmosphere, over a 5 kilometer depth, your exponential decrease will be there. Okay, so that is one thing. And these are all the differences why the atmosphere is different, behaving differently, why the ocean is differing, behaving differently. And when we couple them together, coupled processes, can you give an example of a coupled process? Nothing but our monsoon. We are sitting right at the gateway of this monsoon, right in the monsoon season, middle of the season. So immediately it should occur. People have asked why it is so simple. Some moisture laden wind is coming from the Arabian Sea, and you have all the forecast model. Why you are not giving accurate prediction? If you think, problems will be very problematic. Our problems are problematic, really. Okay, so here actually you can see that the density. See here, today I thought of giving you a lot of derivations, but rather than giving derivation will be available in any textbook. My idea is to inspire your thinking. Okay, there itself we should start, because derivations will be available in any standard textbook. I have the derivation, but I don't know whether if I start deriving everything, you will get bored. I won't get bored, but you will get bored. Really. Okay, so the density is my drawing is not that good with the mouse. Okay, anyway, the air density decreases exponentially like this, right? Okay, what is a linear decrease? Can online participants see this?
Yes, sir.
Yeah, you are able to see. Okay, so exponential decrease means it is something like this, exponential decrease, whereas a linear decrease will be something like this. Okay, so suppose this is the pressure, zero pressure. This is the pressure 1000 millibar, 1000 HPA or millibar. This is, here the pressure is P. This is the top of the atmosphere where the pressure is 0, right? Yeah, pressure is 0. So now let us just think reverse. Suppose the pressure was decreasing, not pressure was, pressure were decreasing linearly, means it is imaginary. Pressure were decreasing linearly. What would have happened? After certain height, pressure would cross. There is no way of negative pressure. Pressure will end, no pressure, zero pressure. That means our atmosphere would have only finite depth, which is exactly finite depth, maybe 20 kilometer, 30 kilometer, that's only. But we know the height of the atmosphere? What is there any such upper limit? Why? Because this is the path. This decreases. Okay. Again decreases. You can draw it to 2000, 3000, 4000 kilometer. Still there will be some air molecules. If the pressure were decreasing linearly, it would have ended up maybe 20 kilometer, 30 kilometer, or maximum 100 kilometer. Within that, it will have exactly finite depth. But because it takes a exponential path, it increases. So we have ionosphere above, even above 80 kilometer, 90 kilometer ionosphere, the D layer, E layer, F layer, all these things happening. And those molecules present in the upper layer will interact directly with the incoming high energy solar waves like gamma rays, X-rays, etc. Produce a lot of magnetic, electromagnetic effects, and it protects our Earth from this type of harmful rays. Okay, so that is one advantage of being compressible. Then we have another fluid. One is viscous or inviscid. Okay, viscous or inviscid fluid. Oh, one more aspect I wanted to just tell you, how the pressure decreases actually with respect to height. At any height Z, the pressure at that height Z is proportional to the pressure at the surface just beneath that air column, right? P0 into, you told that it is decreasing exponentially, so it is exponentially decreasing with an exponent minus G into Z by R T. T actually it is instead of T, it is actually TV, virtual temperature. You know what is virtual temperature, I hope. From somebody from environmental science, do you know what is a virtual temperature? No. Okay. Some atmospheric physics course is also there. No, that is not over. Different temperatures that we use. Oh, okay. I will explain it. Anyway, TV is nothing but a virtual temperature. It is a combination of temperature and moisture amount of moisture in the atmosphere. I will tell you why. So this is the equation that we use when we want to find out pressure at any height Z, provided you should know the pressure at the surface. You should know, actually it is not a TV, it is the average temperature. So I will put a bar over TV, the average layer temperature. Suppose I want to find out the pressure at 5 kilometer, then TV should be the average temperature of this layer extending from surface to 5 kilometer. Okay, that is average. That's why I put a bar there. Okay, this equation is known as barometric formula. Okay, barometric formula you can find out. Now what happens, suppose this exponent within this bracket, its value is 1. That means what? Its value is 1 means GZ should be equal to R TV, isn't it? R TV bar, right? Then what will be Z? RT by G, RTV by, now onwards I won't put, okay, it's very difficult to write with the mouse. So RTV by G. This height Z, yeah, this height has got a particular name. Huh? Yeah, exactly. This height is known as scale height. scale height. I am going very slowly, I know, because there are people from different background. So this is known as scale height. So in terms of scale height, how to clear it here? Something is there clear. This one, no? That one.
Yes.
Okay. So in terms of scale height, now I can write the pressure distribution in the no. Yeah. So in terms of the scale height, I can represent the pressure at any height level Z as P is equal to P0 into, you tell me now, P0 into e power minus Z by H. Z by H. So if you know the scale height, it is very easy. You can find out the pressure at any height as a function of Z. So we know H is equal to RT by G. You put R as 287.053. T you can take something like a 288 Kelvin or even 273 Kelvin, because that is the average height level, maybe 0 degrees Celsius, because at the surface it can vary from 30 at the troposphere, or maybe minus 60, minus 70, something like that. Odd on average, you can take roughly 280 Kelvin or 288 Kelvin. You find out the value of Z, it is RT by G. Okay, so 287, T is also something like a 280. For approximate value, what I am going to do, you can yeah, if somebody has calculator, just do it. 287.053 into 288 divided by 9.8, how much you will get? Something like 8.4, 8.35. Okay, something like 8.4 kilometer. Okay, so that is the scale height of the Earth's atmosphere. Different planets have different scale height, but provided they should have atmosphere first of all. Not that all the planets are having atmosphere. Okay, so scale height is an important concept. What is the meaning of scale height? What for we use it? Pressure decreases exponentially. That's correct. So when we got scale height, when we put the exponent as 1, that means at that time when you put exponent as 1, P will become 1 by E into P0, right? At the scale height, the pressure at any height Z will be exactly E folding, we call it as the E folding height, 1 by E of the surface pressure. Suppose the surface pressure is 1000, then 1 E is 2.718. Okay, 1000 by 2.718. You can approximate it as 3. 2.7 is 3, so almost 1/3 of the height. That means at the scale height, Z is equal to at Earth's scale height, the pressure will be, what will be pressure at a 8.4 kilometer? If you travel something like, suppose this is 8.4 kilometer here, what will be the pressure here? Pressure will be roughly 360 millibar. Okay, roughly 360 millibar. That means 1/3 of the weight is distributed here, 2/3 is distributed below that. That is the simple meaning. Then let me ask you a question. What will be the pressure at Z is equal to 2H? That means 2 times scale height. Scale height is 8.4, so something like 16.8 kilometer. If you travel vertically, what will be the pressure at that 16.8 kilometer or 17 kilometer roughly? P is equal to P0 into e power z by h. Now z becomes 2h. So 2h by h, it is equal to e power minus 2. You calculate, then divide by that. What will be the pressure? That will be something like 135 millibar roughly, right? Yeah. So at 2h, that means 16.8 kilometer, the pressure will be maybe something like 135 or some. Okay, I am giving you a rough value. You see the difference between, or the ratio between 360 and 135, it is again 1/3 of that one. So that means what? For each h, the pressure decreases a fraction of roughly 1/3. Okay. Now at 3h, what will be? Something like 25 kilometer. 3h, what will be the pressure? 1/3 of 135. Okay, something like a 40, isn't it? Close to 40 millibar. So now it is very easy. If you are traveling in an aircraft, you just know the height. You can predict what pressure level you are flying. You know some jet stream is at particular height level. What will be the pressure at that area? So very useful concept. Okay, scale height. So here again, since the air has compressibility, the pressure decreases exponentially. That means what? At the lower level, the steepness is too much, right? But as you go upward, the steepness is very, very small. It never goes to zero, isn't it? Again, if you go by 4h, what will be? 1/3 of 40. Again, you go another 8 kilometer or 8.5 kilometer, 1/3. So it reduces by a fraction, not by a constant amount. That is the difference. Linear difference means, linear decrease means it is of the form y is equal to some y0 minus kx, right? This is a, where k is a proportionality constant. Okay. So here x can be considered as equivalent to height. As you go up height, the y is pressure. So pressure decreases linearly. So it decreases by a constant slope or constant amount k in a linear fashion, whereas in a exponential curve, it decreases by a, not by a fixed amount, it decreases by a fixed fraction. Okay, this has important consequence in distributing the mass within the Earth's atmosphere. So that now we can study different flows arising out of this. Hope this will be sufficient. Now viscous or inviscid fluid, that is another type of fluid. So viscous fluid, we can give an example. High viscous is honey. Okay, something like that. Water generally we consider as inviscous. Okay, because the frictional forces, the molecular friction is very less in this type of fluids. In atmospheric science, generally we don't consider this viscous effect, except when you are studying molecular dispersion and diffusion or turbulence. Their frictional effect is much more, but for large scale weather systems, we generally neglect. So by saying simply neglect, it is very easy, but if you neglect it, that will introduce a small error in the first time step. In the second time step, this error is going to increase, not going to decrease. So after several time steps, this small error can propagate as a big error. Okay, that is what Lawrence says, right? The wings of a butterfly, even if it is small, it can create a storm somewhere else, right? So small errors will finally add up. It has compound interest, as if we are depositing in bank. Okay. So next is steady or unsteady. When all the time derivatives of the flow field vanish, the flow is considered to be a steady flow. That means it is almost like a uniform. Okay, time derivative is here. And otherwise unsteady. So it depends upon the choice of frame of reference also. Next is a very common one, that is laminar or turbulent. That means turbulent flow is characterized by recirculation, eddies, and apparent randomness. So turbulence means random, not regular, irregular, highly irregular. Okay. Flow in which turbulence is not exhibited. Very negligible amount may be there, but for practical consideration, we neglect it. That is a laminar flow. Can you give an example of a laminar flow and a turbulent flow in the atmosphere or anywhere? Cyclone happens. Okay, upper level it will be. Okay, you need not without any weather system, just the flow. Suppose your air is flowing near the Earth's surface. What happened? The topography itself is undulating, highly undulating, with a lot of hills, buildings, trees, etc. But and it offers some resistance to the flow, right? So near the Earth's surface, in the height direction, z direction, the flow is mostly irregular because of the. It is as if water is running through a stream. There will be a lot of rocks turning here there. So you will see all those bubbles and white foams coming out because of this one, and air is getting trapped because of this regular pattern. If you go something like 1 kilometer or 2 kilometer away up in the sky, there is nothing to offer such a resistance except Burj Khalifa or Himalayas, right, or the Western Ghats. So forget about such large obstacles. You go to Arabian Sea, ocean is almost nearly flat. You go something like 500 meter or 600 or 1 kilometer. The flow will be going in a very smooth manner without any obstruction. So that means iso lines, you draw the lines having equal velocities. It will be almost parallel like a railway line. Okay, so they are without turbulence, laminar type of flow, or we say that is a free troposphere, and where the turbulence is maximum close to the Earth surface, it is known as the, what is that layer? Atmospheric scientist. Boundary layer, planetary boundary layer or atmospheric boundary layer, we say, where the resistance to the flow is offered by irregularity over the Earth's surface. Okay, so this planetary boundary layer has lot of a crucial role in dictating the weather, because that layer is the lowest layer of the troposphere, the bottom part of the troposphere, through which energy, mass, momentum, etc. from the Earth's surface is transferred into the atmosphere. All pollution particles, all water vapor. So we all live in which layer? Boundary layer. As a result of man-made activities, a lot of particles are ejected, a lot of construction going on in ENSESS, right? Okay. In the evening, you put an instrument there, you will see how much dust particle, PM10, PM2.5, how much is coming, several gases, emissions, all these are transferred through the atmosphere to the atmosphere through this boundary layer. So it acts just like a interface. Okay. The height of this boundary layer has implications in almost all studies related to atmosphere. Okay, one among them is air pollution. In Delhi, those who are living in that belt, during winter time, you will experience severe pollution, and it becomes so serious that several deaths also happen. Okay, because the boundary layer height collapses, it is very less, so that only within this small volume the pollutants will be trapped. That means per unit volume the number of particles will be much more, concentration of pollutants will be more, and air quality will be affected. So that is the planetary boundary layer dynamics. Just as a corollary, I described it. Now Lagrangian and Eulerian frame of reference, I think you may be aware, but it is not there in the in your syllabus. So I will just quit. But these are two types of frames of reference used in atmospheric sciences. One is the we consider a control volume, okay, and we this is a control volume we fix in the atmosphere. Say for example, 1 meter cube, okay, that is fixed at a particular location. Then you assess the properties of the fluid passing through this fixed volume. Then study its rate of change in this volume fixed at a particular place. Say for example, NCESS source. So such a type of analysis is known as a Eulerian frame of reference. Okay. So it is not moving. This control volume is not moving. Only this material volume is passing through that one. Okay. Whereas now this is at a time is equal to t. Time is equal to t plus delta t. This material volume, its properties will change. It's suppose its concentration, if it is pollution concentration or smoke plume or something, properties will change over time. So, but the fixed volume, the control volume is fixed here. That is the Eulerian frame. Now, in long transport models, this is not good. What we will do, we will take a unit volume of air, then we will attach a coordinate system to that fluid element. Then we move along with that fluid, okay, and study its properties. Hence, our control volume is now moving along with that particle, along with that volume. Then that's a Lagrange approach. Now, basic forces that influence the atmospheric motions. These forces are, if you need any break in between, I will continue like this, but it is your duty to tell. Yeah, okay. So forces that influence the atmospheric motions can be broadly classified as one is body forces and the other one is surface forces. So body forces means it acts on the center of mass of a fluid element or fluid parcel. Okay. For example, you can take gravity, right? Whether it is a cylindrical shape or what to say, some disc or a cubic volume, whatever, it doesn't matter. It acts on the center of mass. So such forces are gravity. Whereas other forces like pressure forces, they act on the surface area. So surface forces act across the boundary surface, separating a fluid parcel from its surroundings. Their magnitudes are independent of the mass of the parcel. Okay, it is proportional to the area of that, like frictional forces, pressure forces, etc. Now, for atmospheric motions of meteorological interest, the forces of concern are fundamental or real forces, then apparent forces. So this is another type of classification. One is a fundamental or real forces. The second one is apparent forces. Fundamental forces are those which exist regardless of our frame of reference. Okay, it's a pressure gradient force, gravitational force, frictional force. Okay, if you look at the friction, it doesn't mind where you are looking from, which coordinate you are referring to. Friction is always acting. But if you talk about Coriolis force, then it is highly dependent on the frame of reference the observer is looking from. So those which account for the acceleration, that is the change in direction. So here Coriolis force actually doesn't affect the acceleration, it affects the direction. Then I have a question. I thought you will ask. In the, oh, are you familiar with the equations of motion? dv by dt is equal to minus 1 by rho del p minus something like that, 2 omega cross r. Okay, those Newton's laws of motion, right? Okay. There we know on the left hand side you have a dv by dt, that is nothing but rate of change of velocity. It is nothing but acceleration. So the total acceleration experienced by an air parcel is contributed by 1 by rho del p minus 1 by rho del p. That means it is the pressure gradient force. Then there is a Coriolis force. Then there is a centrifugal force. Then there is a frictional force, etc. You know the you might have studied the Navier-Stokes equation. Then you know all these terms, different terms, right? There actually Coriolis force is coming into picture. That means Coriolis force some FV or FU. U and V, U is the zonal wind, V is the meridional wind, means the Y wind. U is the zonal or the X direction wind, X wind. When you multiply U or V with the F, that is the Coriolis fact, planetary vorticity, you have a value, isn't it? Let me see that equation is there or not. Oh, it is in some other. Yeah, here you can see dw by dt or dv by dt. This is minus 2 omega u sine phi. This is a what to say, Coriolis effect, right? Because it is related to omega, the angular rotation of the earth. So that means this does have a value, right? This does have a magnitude, and that magnitude is contributing to dv by dt. So still I say that Coriolis force is not changing acceleration or not affecting the speed. Acceleration effect means velocity is also equally affected. Doesn't affect, it affects only the direction. So am I correct or wrong? What is your take on this? Or am I bluffing simply because it is written in the textbook? I just repeat. So as I told, my aim is not to teach you the derivations of all this. We can do it, no, but before that you should start thinking whenever you see or encounter certain equations, how each of those terms contribute to this one in what way. Acceleration. So acceleration is affected by Coriolis force. That means if acceleration is changing, velocity is changing. That means speed is changing. But still Holton says that it is apparent force. It doesn't change. Frame of reference. Yeah. From which point?
We are inside that rotating frame. Will not feel.
No, we will feel. But we are in the earth. We are on the earth, right? We are talking about the monsoon wind, which is coming from Mascarenes High. Once crosses the equator, it turns to right, and the wind flows are southwesterly wind, and we are experiencing it. So we need to consider we are sitting in this frame of reference. It is not that we are sitting at the sun and looking at the earth far from somewhere else. So somebody online, please give your suggestions. Let it be, no problem. You can bluff, no problem. അല്ല എർത്തിന്റെ ഡിസ്റ്റൻസ് മനസ്സിലായില്ല. അതല്ല, കാരണം അതല്ല. Nothing. So yeah. What's your doubt? Gravity is there.
It's actually due to apparent force.
No. Sorry, that is a type mistake. Gravitational force is there. Up. That is a mistake. Sorry. While typing, yeah. That's a maybe I was typing in the night, so just generally Coriolis force and gravity. Gravity should be. Thank you for pointing it out. It is already considered here, gravitational force. Okay. Sorry, that's a mistake. Typing mistake. Okay. So yeah, Coriolis. So I will give it to you for an assignment, and you should all tell me why still Coriolis. Do you know what is Coriolis force? Everybody knows. What is the origin of Coriolis force? Hmm? Rotation of the earth. So simply rotation of the earth means Coriolis force will occur. Suppose earth is cylindrical. Okay. It is rotating from west to east. Okay. Will Coriolis force occur? Will Coriolis force occur? Okay. Now let us think that the earth is a sphere. It is rotating. We are all sitting here. Are we feeling the Coriolis force now? No. No or yes? No. Big no. Yes, we are not experiencing. So why does Coriolis force occur? Particle has to move. Which movement? With respect to that frame, there should be a relative motion. Relative motion. So simply, if we are sitting on the ground, we won't experience Coriolis force. That is good. Now, if the Earth were cylindrical in shape, will we experience that type of? Suppose a particle moves from equator to the poles. The center is equator. This is the pole. Some particle is moving or air is moving from the equator to the pole of the cylinder. Will Coriolis force occur when it is moving in this direction, meridional direction? No. So it should be. It is sphericity. Sphericity, shape of the particle. Okay. Is there anything else? Suppose Earth is spherical in nature. We are moving, but Earth is not rotating. Then will Coriolis force occur? So what are the now three conditions we have discussed, right? What are those conditions? One is the shape, spherical shape of the Earth. Other one is rotation of that one. The third one is relative motion of this particle. Then Coriolis force will occur. For what purpose? What for?
Because of if particle is moving,
Hmm.
it will deviate from their.
Yeah, deviate. Why should it deviate? It can go according to its own decision, prior decision. It can go. So these are all seeds for your in-depth thoughts. Okay, it is just for conserving the angular momentum. But simply by saying that, can a layman understand what is this angular momentum conservation? Okay, you can explain it for physics, those who have studied angular momentum and all. But simply for a common man who has some interest in science but has not studied physics, how will you explain? So the more you learn, the more simpler your explanation will become, right? So you have to think about it because the Coriolis force is not given assigned by Dr. Unnikrishnan. I I thought you all may be knowing. Okay, so these are all seeds for thoughts. You can note down why this Coriolis force occurs. Several such thoughts sparkings we will give in this class. And if you don't know, you can ask me. Otherwise, I will go ahead because I have to finish it at least by today. So now this is a pressure gradient force. You can make a control volume having delta x, delta y, and delta z sizes. Then it's a total volume is delta x, delta y, delta z. We are going to derive the pressure gradient force acting on this one. But you know all this one. You know the pressure is acting in this direction. Suppose pressure is acting in this direction. What is the net pressure acting on that area? Area is here. It is delta y. This is delta z. So this area is delta y into delta z. Whereas this area is delta x into delta y. This is delta y into delta z. This area. Likewise, you can calculate the total force acting on that one, then find out the resultant one in the x direction, the net force in the x direction, net force in the y direction, net force in the z direction. You can all add up together, then finally you will get this result. Shall I go deep into this one? Then I will be able to finish only this portion. So this is a very simple mathematics. You can just find out. So per unit volume, that's why rho is appearing here. Del P. What is del P? Gradient, right?
ഇത് മുന്നീരെ പരിപാടിയാണ് ഈ ക്ലാസ് ഒക്കെ.
Sir, you are muted.
Oh, since when?
Yeah, now it's fine.
No. Since when I was muted? Now only or for a long time?
Sir, you are muted.
Oh, 1 minute. Okay. Now nothing has been covered within this 1 minute, so no problem. So next is a very fundamental force, that is gravitational force, and that is also in high school standards we have studied. So I will go quickly wherever possible. It's like a highways, wherever traffic is less, I have to cope up with the time. So gmm by r square with the unit vector r by its magnitude, that it will show the direction. Okay, so minus gmm by r square, and you know the universal gravity constant, etc. So regarding gravitational force, one important thing is you know the difference between gravitational force and gravity. What actually we experience is not share ചെയ്തിട്ടില്ല. ശരി. മൈക്ക് എന്താ മ്യൂട്ട് ആവുന്നത്? അത് തനിയെ ഓട്ടോമാറ്റിക്കലി ആവും അല്ലെ? ഓട്ടോമാറ്റിക്കലി ആവുന്ന ഇല്ല, ഞാനൊന്നും പ്രശ്നം, ഞാൻ ഈ മൈക്ക് ഇത് മാത്രം.
Now it's fine.
Okay. So this is the how we will find out the it is actually a tangential force. This viscous force acts in the tangential force required to keep the fluid in uniform motion at the upper plate is proportional to the area of the plate the velocity u0 and the inverse of the distance separating the plates 1 by L. So the viscous force can be calculated as mu into A, it is the area, into the velocity divided by L, where mu is the dynamic viscosity coefficient. Likewise, so I am not going through all the time steps or all the derivation steps. So this is how we address the viscous force. And when you divide the dynamic viscosity coefficient by its respective density, it becomes a kinematic viscosity coefficient. So generally we mu by rho is known as the kinematic viscosity coefficient. Next is centripetal acceleration and centrifugal force. This is also known to everybody, isn't it? When we take a curved path, there will be always a tendency to move away from that path. In which direction? In a tangential direction. So this is the center. This fellow is rotating in this counterclockwise direction with an angular velocity omega. Then this is the one. The rate of change at this one will give its a tangential velocity, right? So we can calculate the rate of change of this one, this velocity, that is nothing but a dv by dt is equal to minus omega square into r, where r is the distance between the center of this rotation and the outer ring. So I'll know quickly. And when it has a tendency to move tangentially outward, to prevent that, we should apply certain force to keep it intact, right? What is that force? The opposite force? Centrifugal or petal? Centrifugal. Sorry, centripetal force. Centrifugal is opposite. This is what exactly happening in satellites orbiting in the elliptical orbits, right? Certain forces are required to keep it intact. What is that centripetal force in the case of a satellite? Gravity. We cannot keep a rope and keep the satellite all the time. It is gravity. Gravity is offering that centripetal force. And you know why we keep the roads banking of curve? Okay, because there will be some force always directed in this one, so that the vehicles won't skid. But what about a train making a curve? Is there any such banking? Banking is a train taking a curve. Have you observed? Is there any like a banking of this, or is it both are in the same plane? Yeah. When we are moving at a faster rate, maybe 80 kilometer, 100 kilometer, we won't feel it. But if a train stops in a curve, you can see still it is curved. But that alone is not sufficient for keeping the train on the rail. There is something else also, very, what to say, magnificent engineering you can see. What is that one? It is not related to physics, some engineering marvel. Have you seen the wheel of a train? How is it? Tell me. Yeah, very good. I hope I am not muted. Where is that whiteboard? Yeah, okay. So if you consider the cross section of a train wheel, its surface, outer surface is not flat. Instead, yeah, one side is, suppose this is the wheel, inside. Okay, it is not flat like this. You hope that it is flat like this. Okay, and here this wheel is, my drawing is okay. This is what we expect. Sorry, this should be inside. I should have drawn differently. This way. This part should be like this, right? This cutting is inside. Okay, so this is how the trains wheel look like. This is what we expect, but it is not actually. It's something. For example, this wheel I will draw here. It is something like this shape. Now next time when you travel by train, don't peep into the train, but look from a safer distance. You can see that this is the conical shape here. Okay, this conical shape will, this wheel. Okay, this conical shape will always from both sides when it is coming, it will be like this. Okay, so this is the rail now, right? Oh, again it should be different. Um, this side. Okay, this is the rail now. What is the advantage of this conical shape? When it is negotiating a turn, suppose it is taking a left turn like this. Okay, when it is taking a left turn like this, the outer wheel is this one, right? This fellow will try to move in a tangential way, going out. But when it is moving in that direction, the conical shape will allow to put it in the original one. Okay, and still it will be moving in this direction, so that here this wheel also, this left wheel also move towards right slightly, so it is encountering a small radius of rotation here. Okay, here it will be high radius of rotation simply by that conical shape. Now both the wheels are not having the same radius. That's the advantage. Okay, the right side angular velocity, sorry, linear velocity will be more compared to the left side, because left side the radius is small, so linear velocity is small. So there is effectively a shear coming in picture, velocity shear. This is left wheel, this is right wheel. Okay, so this shear will, if there is some flow like this, the flow will always have a tendency to turn towards left. This is a dou v by dou x or dou u by dou x. In the vorticity you might have, I will discuss vorticity, cyclone, etc. Okay, so this is very beautiful concept, because all this weight otherwise would have moved away, but simply by doing this one. And there is, of course, there is a banking in the curve also. So both of this will try to prevent the train from derailing. Hope I am not muted. Now I told you there is a difference between gravity force and the gravitation. Okay, so in simple terms, I won't go too much this one. Suppose initially the earth is perfectly a sphere like this. Okay, perfectly like a sphere. You take the one quadrant of a sphere. But here again the problem is, this is the angle of the radius of rotation for this particular latitude. Say for example, if it is some 60 degrees north latitude, the distance, actual distance from the axis of rotation to the surface is r, isn't it? This r, and here also this is r, this is equator, right? At the equator, this is also r. Which r is more? At the equator, or equator is the biggest latitude, but the actual distance, the radius of rotation, right, is decreasing as we move towards the poles. Okay, then the centrifugal force is omega square r, right? So where the centrifugal force will be more, in the poles or at the equator? Because r is more at the equator, so of course centrifugal force is more at that means it is pulling all the mass, let us go outer, into outer space, right? But gravity keeps it intact. So but still the centrifugal force is much more. What happens? There is a bulging outward force, bulging at the equator, and there is a contraction of this because more mass is now concentrated towards equator, so there is less force acting exactly at the pole. What is the centrifugal force? Exactly at the 0, so there is no one. Okay, but here more pulling, so the earth's shape will now change, or its shape will be deformed with a bulge at the equator, just like our stomach somewhat bulging after fat deposition. Okay, equator will be bulging and the poles will be compressed. So the shape of actual earth is known as geoid shape. Okay, now what happens here? I can put omega square r is the, actually if the earth were purely spherical in nature, gravity, or not gravity, this g star, gravitational force, should have pulled all objects exactly towards the center through this g star line. But now you see here there is a force acting outward, radially outward. So omega square r is there. So this is a vector, g star is a vector, omega square r is also a vector which is trying to out. So the resultant is g. Okay, g is this much only. You see, g is this much only. So this g is the effective gravity that we are experiencing. Okay, so that is gravity, the other one is gravitational. So this is effective gravity. Hope everything is, now you read some good books, you will get a lot of this one. But exactly at the poles, what will be effective gravity? There is no centrifugal force, so g and g star will be same, isn't it? That is the corollary. So we now define some gravity force, which is represented as minus y minus, because it is acting vertically downward. So vertically upward is plus, that is a convention we use. Vertically downward is minus, so minus g. G is the, this small g is the magnitude, this thin g, with a k vector. K vector is actually indicating the direction. Okay, so it is minus k, actually minus k into g. That is nothing but the g star plus omega square. Now there is one thing that is not as a geopotential. Have you heard about the geopotential? Sometimes it is very easy to describe the properties of fluids in terms of its energy. Okay, rather than mentioning its height level. Then if we know the height level, what potential level it is situated, it's very easy to describe it in terms of geopotential. I will describe it later on, but be familiar with the term geopotential. Phi is defined as G into dz. Okay, or if you bring this dz here, it will be d phi by dz. So that will be minus G. That's why it is called del phi is equal to minus G. Or gravity can be represented in terms of the gradient of a potential function phi, which is just the geopotential. We will learn it after some time. Now our fellow has come. Coriolis. Again, I am not going to describe its derivations, but just have given enough sparks for igniting your thoughts. Now tell me, why should an object moving relative to the earth experience a deflection in its path? Deflection can be in any direction. If a particle is moving in the x direction, it will be deflected towards y direction. If it is moving in the y direction, isn't it? In general, we say a particle moving in the northern hemisphere will be deflected towards right of its path, and vice versa for southern hemisphere. It will move towards left. Why? Why? Coriolis. Why Coriolis? It is deflecting. Okay. What is the reason? See, without knowing the reason, if I tell you all these equations, you will immediately vacate this classroom. Then it will be very easy for me. I can go back. Okay. We gave one principle that it should be for the conservation of angular momentum. By saying that, what did you understand? Simply don't by heart the things. Okay. So what is your take on this? Shall I describe all these equations and make you mum? That means you won't understand anything. Or yeah, this is Coriolis force. So I can leave this PPT here. You can find out the derivation. All the steps are given, assumptions are given. No problem, nothing. But why should it deflect is a major concern. For x direction movement, y direction movement, and even the vertical movement, even though when it is moving in the vertical direction, there is a Coriolis force acting, but that is its magnitude is negligible. Generally, we don't consider. But theoretically speaking, we have to consider if at a larger velocities, this can have impact. So why? First of all, it's a deflection, right? Let me explain you why we should feel. Where is Coriolis force more? You might have studied at the equator or at the poles. 2 omega sin phi, F is equal to 2 omega sin phi, where phi is the latitude. Okay, so at the equator phi is 0. 2 omega into sin 0, 0. 2 omega into 0 is 0. That means at the equator 0. Why? That's based on mathematics. Anybody can do it. Why it is 0 at the equator? Why it is maximum at the poles? For that purpose, you can imagine. I will draw it something like, okay.
So, can you guess?
Yeah, you please. Your guess is required. Yes.
Path-related concept is there.
Yeah, okay. Can you explain path-related concept? how it is coming. No. Inertia. No. Inertia will be there, irrespective of whether it is deflecting or not. Online participants, I am not muted, right? Yeah, okay, mic is on. All the time I have to check. Suppose this is Earth, right? Okay. I will, right now I will not tilt my angle, Earth angle. So this is equator. Okay. Let us take some 45 degrees, and here it is spinning around this axis with an angular velocity omega, right? Yeah. Now suppose you are standing here. Who? Sneha is standing here. Okay. So Sneha is standing here. Okay. Today, right now it is 12:45. After one day, she will make one perfect rotation. And where she will be back? Back at the same place A, right? So what she is doing? This is her head. She is moving in a circular way, right? Nothing else. With her foots on her surface, head away from that one. Likewise, she is rotating. So when she is coming here, again she will be here at the opposite side, right? She is just making a, it is not actually rotation. I would say that she is, suppose this is the, A is the radius of the Earth. A, she is making actually a revolution around the Earth axis with a radius A. It is, for her it is not rotation. It is a revolution only. Now what is your name? Abhinav. Abhinav is sitting here or standing here. Okay. Abhinav is standing here. Okay. During this exact 24 hours, what Abhinav will do? Will he make a revolution with a radius R, or what? He will not move. Instead, he will just spin like this. One complete spinning like this. Okay. Without any revolution. Isn't it? Because here A is what? A is A, not A. This radius is equal to A. R is equal to A. Here R is equal to 0. So he cannot make any what to say revolution. He is making a spin. Spin is actually what? Okay. It's just like you take a pen, rotate, spin it. That's all. Spin. So now tell me, Abhinav or Sneha, who is spinning and who is not spinning? Abhinav is spinning. Sneha is not spinning. She doesn't feel a rotation of the Earth. She will feel through day and night. Other than that, she will not physically feel that she's okay. Okay. Okay, then what's your name? Amrita. Amrita is now sitting at a 45-degree latitude. Okay. How she should be standing? I will use another color. She should be standing with like this, right? Amrita is here. Isn't it? Everybody should be pulled by gravity towards the center. Okay, so she is making an angle 45 degree with respect to whom? Sneha. This is Sneha. This is Amrita. This is Abhinav, right? Abhinav. What Amrita will feel now? Tell me. she is partly spinning. Okay, if she has to be exactly partly, it should be at a sine 30, then only sine 30 is 0.5, right? So it's instead of 45 degree, if she is standing around 30 degree north, sine 30 is 0.5, right? So she is suppose 30 degrees, she is partly spinning, partly revolving. Now you understood why a person sitting at the equator doesn't feel the effect of spin or rotation of the earth, whereas a person who is just standing right at the poles on any hemisphere is feeling rotation, not the revolution. So this is the very fundamental thing. Now this is not enough, you have to think, because now the rotation will increase as the angle of latitude, right? Sine angle, as the angle is more, spinning will be more, likewise. Okay, so this is you might have got some idea about spin and the other one. Then secondly, why a particle, this sound will always be there, or so until now we have discussed that the radius of all these latitudes, okay, is changing. Maximum at the equator, are some ghost is playing. Okay, some memory. Okay, so the radius of, we can say something like a radius of gyration, something like that. Okay, it is, suppose this is a, what is this distance r? R is equal to, this is the angle of this latitude, making an angle phi. Okay, so phi, then what will be r? R is equal to a, in terms of a cos phi. You drop a line something like this, then this is nothing but your r, that r is here, so r is equal to a cos phi, or it is nothing but the projection of this line on, or projection of this equator at that latitude, we can say in a reverse projection, r equal to a cos phi. Okay, so it decreases towards, at exactly at the pole, cos phi is cos 90, 0, so there is no r. That is, you got that idea now. Now suppose this is India. Okay, this is NCESS. Now Abhinav is throwing a stone towards somebody who is sitting here. He is throwing a ball towards this location. Okay, now comes the problem. What happens? This is r here. Okay, suppose earth is not rotating, then what will happen? Abhinav will launch this rocket or ball, it will hit exactly at the intended points, right? But problem is, earth is simultaneously rotating. Okay, suppose it takes 1 hour to reach a stone from here to here, this latitude, this much 1 hour it will take. Okay, 1 hour. By the time Abhinav launches a stone or rocket from this place, he is moving, this Abhinav is now rotating, right, or moving in a circular radius with radius as a, right? So he has an angular velocity. What will be the corresponding linear velocity? You can calculate anyway. Arc is equal to how much he will. Okay, if he makes an angle uh, d lambda, d lambda, that is equal to a. Okay, you can simply use the equation arc is equal to radius into arc is equal to radius into angle. Simple relationship. Okay, so what will be the linear velocity? This is the linear velocity tangential to the circle at that point. What will be his linear velocity? You can calculate. Earth's angular velocity we know. So how much does the earth rotate? At what speed earth is rotating? Angular velocity everybody knows, right? 7.29 into 10 power minus 5 per second. Can we visualize it? No. If we convert it into linear velocity, we can visualize. How much it would be roughly? You can think that the radius is 6,400 kilometer roughly. Okay. Then 2 pi r is the distance, total distance traveled. So you multiply by 6.28 2 pi, right? Into that one. Something like a 40,000 kilometer per for one complete revolution. So you divide this 40,000 divided by 24. You will get something like a 1,500 or 1,600 kilometer per hour. That means within 1 hour, yeah. By the time the ball, how much time I told you to reach up to this latitude? 1 hour. By that time, Abhinav would have moved 1,600 kilometer away towards this direction from west to east, right? So eastward he might have moved. Now no longer he is here. Abhinav is now his new position is somewhere here. Okay. Whereas here also this place also will move. Where it will move? In the same direction, but with a small linear velocity, because there the 2 pi r is different, right? R is very small. There is a cos phi factor coming into picture, so it will decrease by cos phi, that much factor. Are you able to follow me? Okay, so if suppose here it is he is moving 1,600 kilometer per hour, that means within an hour he will move 1,600 kilometer. Here it may be, say for example, for simplicity, only 600 kilometer. Let's assume. Okay. By the time he launches a stone from here, this stone also would have acquired the same linear velocity as that of Abhinav. Okay. So the problem is, as it moves towards smaller and smaller radius, right? The place would not have moved that much. So to reach that same place, for Abhinav, it will appear that the he is moving towards right. So the part for him actually, how should I draw it? That's what I was, as if it is moving towards right. For a person who is observing from here would think that it is moving because of the relative change in the linear velocity experienced by the object. As if there are some good I can't draw it here, but let me see some good YouTube videos or something like that. Okay, so when we look uh, it appears something like turning towards, for us it will appear like this, it would have turned to the right of its path. Now similarly, if he is launching a stone or rocket towards this side, it would appear to be turning towards the left of its path. So by moving this one, the angular momentum is now conserved. That is the one. But suppose Abhinav is now throwing a stone in the east-west direction. Why should it deflect? When it is moving in the meridional direction, we can see that the linear velocity is different for different latitude, or meridianally the linear velocity changes. He is now throwing in the x direction along a particular latitude. Why should it deflect towards right or left? What is the physics? It will deflect. Fourier's force has x component, y component, z component, right? It should deflect. The simple physics is, if he is launching a rocket towards east, Earth is also having an eastward velocity. So the stone would acquire the velocity with which he is launching plus the Earth's already eastward velocity. So it will be added to that, right? But if he is throwing a stone westward, then what would happen? Earth is having that linear velocity towards east. He is launching towards right. So there will be a cancellation. So total velocity will change. So to conserve angular momentum, it should either drift towards right. I mean, in the northern hemisphere, it should right towards right. Right means it is moving, by deflecting right means it is moving towards a small radius of the rotation, right? Yeah. Similarly, if he is doing the same thing in the southern hemisphere, it should rotate to the left. Now if he is moving or throwing a stone or rocket towards east, that should reflect again to the left, right? Here if he is throwing a stone, it should deflect towards right. That means it is entering into a different, now it is equivalent to what we said earlier. It is changing its radius of rotation. So angular moment is concerned. Then tell me, if he is launching a rocket in the z direction, why should it deflect? Are you able to imagine? You have to have a visualization, otherwise this is very difficult. Or you can, I don't know whether some good YouTube videos are there. If I get it, I will send it, but very rare, because these things require some abstract ideas. You have to run along with me. If he is launching a rocket upward, or he is launching a rocket from upper height to downward, which direction it should deflect and why?
Rocket motion or rotation.
That's rotation.
That's a rotation only, but same thing you can see here. If he is launching a rocket, I will use a different color, red. Okay. Oh, this is I have used. So orange I will use. If he is throwing a rocket, what will be the radius of rotation? A plus some, suppose this is the height, A plus h. Okay, now its angular velocity should be not omega square or r, omega r plus a, r plus h. That will come into picture. So it will be in a bigger one. So accordingly to conserve, it will see which direction I should move so that it is conserved. It will take that path. Okay. If he is throwing downward, then it will always be A plus minus H, that one. Okay. Because H is now decreasing. Accordingly, it will think in which direction I should move so that total angular momentum is conserved. So this is the very principle of angular momentum conservation. When we say angular momentum conservation, we didn't think of this one, but now we know why should it move, which direction should move. So just be logical, then mathematical. Finally, we will get all physical explanations.
You can conclude for the session.
Session. Oh, very good. So I am going very slow. Sorry. Okay. So yeah, I concluded. Thank you. Okay.
Stop sharing.
Stop sharing. Okay. So when we will reassemble